Starting today, we will proceed towards writing general relativity in the language of differential geometry. It will take a few lectures. We could very well ask, why do we have to do this? We can do general relativity and Einstein equations without using differential geometry, just using coordinates, vectors, contravariant and covariant vectors and tensors. We can do that. But this is the equivalent language. The least that could be said is that it's very pretty. It tells us how to think of vectors and tensors without having to think of coordinates. These are entities which don't really need coordinates for their definition, and that's the language we want to develop. And it also works for other forces, electrodynamics and other standard model particle physics forces like weak force and strong force. Especially if we go to the combine this with the language of fiber bundles, you begin to see a unity. It looks very abstract and painful at times and distasteful even when you see it in the beginning, but as you slowly get used to it, it's actually very easy. It can be taught at the undergraduate level, the ideas of differential forms. And so we strive to make it look nice and interesting. Okay. So let's start by remembering. So some of these things, most of this you know already. And also Patrick did a lecture, full lecture on differential forms, no? So this, in that sense, today's talk will be a repeat, but from next lecture onwards, we'll see that whatever Patrick is doing with tensors and in coordinate systems, we'll do the same thing in the language of differential geometry. So talking of spaces, there we must distinguish between three kinds of spaces: differentiable manifold, an affine geometry, and a Riemannian geometry for our purposes. A differentiable manifold, think of it as space-time with coordinate systems. The different coordinate systems can be used. We know how to transform from one to the other, and that is essentially what we would mean by a differentiable manifold. It is smooth. If you introduce parallel transport, connection and curvature, it becomes an affine geometry. So notice I have not introduced the metric. I can talk of affine geometry and geodesics without talking of the metric. And the connection and curvature are enough. And then if I introduce the metric, the affine geometry becomes a Riemannian geometry. We need the metric because in Einstein equations, the metric gives the potentials whose gradients give the gravitational force or gravitational field, which is the connection. The connection is the gradient of the metric, and if the metric is present, the connection is supposed to be compatible with the metric. In other words, the covariant derivative of the metric should vanish, and that imposes a constraint on the connection. It becomes related to the metric. That's the Levi-Civita connection. For the components we call the Christoffel symbols. Okay. So what is a vector? So think of the set of coordinates Ct, x, y, z of an event in four-dimensional space-time. You have t, x, y, z, you have an origin, and there is an event that takes place at t, x, y, z in the space-time diagram. Draw a line joining the origin to the point at which the event takes place, directed from the origin to the event. That line is a four vector xi, whose four components are Ct, x, y, z. Yeah? And we know how this transforms under Lorentz transformation, that you know. So first we begin with flat Minkowski spacetime, then we go to non-inertial coordinate systems, and then finally to curved space. In general, a 4-vector AI is a set of 4 quantities which transform like xi under transformation of 4-dimensional coordinate systems. So I have defined the position 4-vector xi. I know how its components transform under Lorentz transformation. A 4-vector AI other than the position vector is a set of these 4 quantities which transform like xi under transformation of 4-dimensional coordinate systems, which same is true in Minkowski frame, Minkowski coordinates, Lorentz transformations, as well as more general coordinate systems. You know how xi transforms to xi prime is del xi prime by del xj xj. That you understand, yeah? So a 4-vector, also known as contravariant 4-vector, will transform the same way as the position vector. For contravariant, we write the indices upstairs. Yeah? We call this a contravariant vector AI. The covariant vector A subscript I is defined as, this is the definition of a covariant. Covariant vector corresponding to the contravariant vector A upper I. A lower I is same as A upper, and A1, A2, A3 have a change of sign. Okay, that's a covariant vector. And since 1 forms are coming, a 1 form is a covariant vector. Just want to make a picture. If you are first time being introduced to forms, a 1 form is the same thing really as a covariant vector. If you do this contraction AI, this is Lorentz invariant. Why? You can easily see that. What is AI? It is basically A0 square minus A1 square minus A2 square minus A3 square, and that is a Lorentz invariant quantity. And you can check, so hence this guy is called a 4-scalar. AI upper, AI lower, it's a 4-scalar because it's Lorentz invariant. It does not change under Lorentz transformation. So is AI BI. Take some other vector BI, write A1 upper, B1 lower, plus A2 upper, B2, and so on. You can check that this object is also a 4-scalar. It's a Lorentz invariant. It will transform the same way as this object AI. So this is a 4-scalar. This is also a 4-scalar. A 4 tensor of second rank, 1 upper index, 1 lower, for example, transforms under coordinate transformations like products of components of 2 4 vectors. So T upper I lower j will transform the same way as A upper B lower. Is that okay? Are you okay with that? So if you have a few upper indices, you will get, so depending on how many upper indices and lower indices you have, you will get tensors of different ranks. So this is second rank, and more precise, I would call this a tensor of rank 1, 1. 1 upper, 1 lower, yeah? So stop me anytime. So this is very easy to understand what a tensor is. And this object we are going to soon start thinking of in a coordinate independent way. Right here I am depending on components, right? This has these components, for example. Tij will have 16 components in 4-dimensional spacetime. I want to start thinking of this object without its components, as if it exists of its own without referring to the coordinate system on which it lies. The unit 4 tensor delta ki satisfies delta ki ai equals ak. What is delta ki? If k and I are the same, delta ki is 1. If k and I are different, delta ki is 0. Okay? No minus ones in delta function. Yeah, be careful about that. Delta k upper, delta I lower is 1 if both the indices are equal, 0 if they are not equal. Then it is easy to check delta ki ai upper is ak. You just do the sum because this is being summed over, and this will not vanish only when k is the same as I, right? So a1 delta 1. So if I is, you see what it means, right? Let's see. a1 delta k. So you can work this out. Suppose I take k equals 1, so delta k1 a1. So this is giving me a1. If k is 1, I will get a1, right? Is this okay? By raising one index or lowering the other index, for a moment I move this up. By raising one index or lowering the other index in the delta function, in delta ki, we get the metric tensor G upper ik, or that's the contravariant form of the metric tensor. This is the covariant form of the metric tensor, having components diagonal 1, -1, -1, -1. What does this mean? You can check. I have delta ki. If I take the lower index up, whatever tensor I am going to get, there is no change in sign for the 0th component, but there is a change in sign for the spatial components. Similarly, if you bring the upper index of delta ki down, you will get this. And right, you can so my gik upper as well as gik lower are of this diagonal form, and this condition is satisfied. You can check that, right? Because that is very obvious, because the A lowers have a sign change for the spatial part, and that is what this is going to achieve. Okay? Please stop me if there are any questions. Yeah, this is fortunately still very basic. You have seen this already many times. Okay, so now we gradually move towards the language of one forms. Okay, what next? The 4 gradient of a scalar is the 4 vector del phi by del xi, the time partial derivative with respect to time, and gradient of phi with respect to space. This is the 4 vector. It's a covariant 4 vector. We just defined a covariant vector. Why is this covariant? Think of this differential d phi of the scalar field. What is d phi? It is del phi by del xi dxi. Now d phi is a scalar. Yeah? dxi, this is a coordinate differential. It's a contravariant vector. Because x, the position vector is a contravariant vector, this is a small increment in that. So this is a contravariant vector. If I want a scalar, I have to multiply it by a covariant vector. You see that? Del phi by del xi is a covariant vector. So the gradient is a covariant vector, and the covariant vectors are to be thought of as one forms. So the gradient will be a one form. We'll see that in detail. That will be the gradient one form. The gradient one form is an example of a one form.
Shouldn't be there a minus sign in the spatial point?
Somewhere did I do this right? No, I think, why is this not okay? Now it depends.
Can you go back to the previous slide where, according to the convention,
This, I think, is the definition. You will pick up a minus sign if you want to form a contravariant version of the gradient vector.
if you define this way, then
that one will have a minus. I think this is the correct definition. Okay. The operators of differentiation del by del xi with respect to coordinates xi are components of a covariant vector. For example, the divergence is a scalar. So, del by del xi is a covariant vector acting on the contravariant vector ai. This object, the 4 divergence, this is a scalar. Yeah, does not change under coordinate transformation. And just of note, we will need this. Del by del xi of aj is a number. Yeah, these are, you get different numbers for different values of I and j, but each of them is a number at a given place. Okay. We must learn to think of a vector as a coordinate independent entity. We must learn to think of a vector as a coordinate independent entity. For example, the velocity vector u. So, okay, this is now, so I will sometimes go to 3-dimensional, sometimes come back to 4D. So, please bear with it. If you have a curve in 3-dimensional space and you draw a tangent to that curve, or if you have velocity vector in 3-dimensional space, you will expand it in components like this in 3D, okay? Or you can do something analogous in 4D. This has components E0, what am I doing? Sorry. It is 4D. I'm sorry, I'm causing a confusion. Velocity vector spin space time expanded in the coordinate basis E0, E1, E2, E3 has components U0, E0 plus U1, E1 plus U2, E2 plus U3, E3. But we want to think of this, it exists independent of coordinates, okay? Okay, a differential one form omega, we'll use symbols like Greek symbols like omega for one forms and Roman symbols for vectors. A differential one form omega is a linear function of a vector input. That's the definition of a one form. A one form is a function of a vector. You act a one form on a vector, you will get a number. Okay? So, I hope this is clear because this is what it is. A two form will act on a pair of vectors, except that will also be antisymmetric by definition, but you get the picture, yeah? What we call a covariant vector is actually a one form. We will see that more and more as we go along. The set of one forms is closed under addition. You add two one forms, you will get a one form. And under multiplication by constants, yeah, you can have a one form omega, you can have a one form k times omega. If omega acts on k, if omega acts on k times v, it is k times omega v. If omega acts on v1 plus v2, it is omega v1 plus omega v2. So closed under addition and multiplication. Hence, it forms a vector space. One forms also form a vector space dual to the space of vectors on which the one forms act. Yeah? The vectors form a vector space. The one forms which act on these vectors also form a vector space called the dual vector space. We can think of a vector v as a function that acts on a one form omega. We right now talked of one forms acting on vectors. I can also think of vectors acting on one form. There is a duality, there is a balance, there is a symmetry. What's the definition of a vector v acting on a one form omega? This is the definition. Is the same as this, by definition v acting on omega is the same object conceptually as omega acting on v. Okay, so if somebody asks you how much is v acting on omega, so it's the same as omega acting on v, and omega acting on v we have already defined. Because of this symmetry, we also denote omega of v as this contraction omega with these two wedges on both sides. Omega of v can also be denoted as omega comma v wedge. It's a contraction, which will be equivalent to a dot product. We'll come to that. Basis one forms. Given a basis Ej for the tangent space at a point P on a manifold. So what is the tangent space? I am at some point on space time. I draw 4 basis vectors in terms of which all vectors can be expanded. So E0, E1, E2, E3, like here. So E0, E1, E2, E3 are basis vectors. They have unit magnitude. Yeah. Given a basis for vectors such that V is Vj, Ej. That's how I expand a vector in the basis. Define a dual basis for this tangent space T star P of one forms at P such that omega I of V equals Vi. So this is my basis. Now omega i's are the basis one forms. This is the full basis. What's the definition? Omega I acting on Ej is delta Ij. So what was a one form? A one form acts on a vector. So this one form is acting on a vector. The basis one form acts on basis vectors in such a way that the resulting number is 1 if I and j are equal. The resulting number is 0 if I and j are very intuitive, right? Yeah. So this means that omega I of V is Vi. A basis one form acting on a vector picks up the corresponding component. Well, that's very easy. V is Vj Ej. Put Vj Ej here. Pull Vj out. Omega I Ej is delta Ij. Vj times delta Ij is Vi. So I hope this is clear. It's very intuitive. Once you start getting used to it, it's very intuitive. You see the duality of vectors and one forms. So just as there's a vector space basis for vectors which gives us the tangent space at a point, you can do the same. You can do a vector space tangent space T star P of one forms which will be labeled by this basis forms shown here. The corresponding thing to the basis Ej is this dual basis omega I. Is this okay? T star P is dual to the tangent space Tp, and if you remember the language of bundles, all the tangent spaces together form a fiber bundle which is known as the tangent bundle. It's a vector bundle which is called the tangent bundle. Okay? So what was a bundle? It was a collection of fibers on a base space. Base space was a space-time manifold. At every point there is a tangent space. The tangent space is the fiber space, and it is a vector space. So that kind of a fiber is called a vector bundle. The collection of all the tangent spaces at all points is the tangent vector bundle. It's called a tangent bundle. Question: can we also think of one forms and vectors as operators with respect to each other? Yeah, that's a good point. Yes. Operator in the sense of they act on each other and they yield a number. So normally operators are reserved for matrices, but operator in the sense of acting on each other. Yeah. Okay. So there is a tangent bundle and there is a cotangent bundle. If you have any confusion about this bundle idea, just stop me and ask. Bundle is nothing but a collection of tangent spaces. That's the tangent bundle, and there is a cotangent bundle. Okay. Now I want to talk of components of a one form. Vector components I understand. So obviously in the similar way, components of a one form will be in the one form basis omega I. That's okay, no? And right, so how do I write components of phi? Phi acting on the vector v gives me Vj, vector v is expanded in the basis as Vj Ej. Pull the Vj out, this is phi of Ej. And what was Vj? Vj was what you got when omega j acted on V. So replace Vj by omega j acting on V and phi Ej. Okay, so we slowly get to now components of phi. You can clearly see that phi Ej are going to be the components of phi. We should eventually question. Explanation of bundle would be better. What does this mean? I should explain the bundle. I did it, please, last time. So I'll come to it. I'll come back to it. Okay. Yes. You want to know what's a bundle, but we did it yesterday. So quickly, there is a base space M. At every point, there's a fiber F, which is another manifold. F and the base space B along with the fiber space F, when you take all the fibers at all points of the base space together, that is called a fiber bundle. If the fiber space is a vector space, it is a vector bundle. Yeah. Okay. So phi of V is phi of Vj Ej. So Vj phi Ej, and Vj is omega j V times phi Ej. So phi Ej are going to be the components of phi. So little more, just hang. And this V I would like to get rid of. I think of forms as acting on vectors. A vector can be arbitrary. So when I write the basis description of a one form, the vector V should not appear. Okay? So let's look at the next line, then it will be better. Components phi j of phi are by definition phi Ej. That you have seen here. Why are they components of phi? Because phi Ej times omega j. That's what a basis is, no? Omega is the basis. Just as here Ej was the basis and Vj were components, here omega j is the basis and whatever is left are the components. V we will soon remove. So components phi j of phi are phi Ej. In other words, phi of V is phi j omega j acting on V. This is very clear. Just as I write components of V as Vj Ej, components of phi are phi j omega j acting on V. So now remove the V because V is arbitrary. So I am left with phi equals phi j omega j, which is equal to phi Ej omega j. So so I can write phi like this, phi j omega j. These are the components of phi. Phi j are components of phi. How are they defined? The number that you get by acting phi on the basis vector Ej is the component of the form phi along the jth direction.
Okay. That way of putting it, phi of Ej omega j.
Last line.
That Ej, the index comes in the bracket as a functional form.
Yeah. Differential forms, one form acts on a vector. If the one form phi acts on the vector Ej, I get a number phi j. That is the component of phi in the jth direction. And along with that component, this is the basis. This is the expansion of phi in the base. What I'm trying to say, I say the basis of expansion of phi is phi j omega j. Yeah, but what is phi j? I can relate phi to the vector basis that I have already defined. If you don't want to talk of the vector basis, you can say this is how I expand phi. Just as I expand a vector like this, I expand a one form like this. But we are saying, okay, I have been given a vector basis. and the vector basis is related to the one form basis in this manner. If this is true, then this has to be also true, that phi j is Ej. But yeah, you get the picture. Any questions? Please try to digest it slowly. It's nice and simple, but just takes some time.
I have a question.
Yeah.
So we are dealing with any arbitrary basis Ej.
Yeah.
So what if it becomes orthonormal basis?
Yeah, that's okay. What is the problem?
What spatial things we will get? With this a general.
Yeah. I mean, I don't know what's the answer to your question. Right. So this can be orthonormal.
In particular also.
Yeah.
Because sometimes I think working with orthonormal basis will give us some more mathematical properties.
A good point. I need to think how to answer that correctly. But right now, given that orthonormal basis is what I have in mind. But this doesn't have to be just that. Okay, so this all right. Vectors, vector components, vectors thought of as without components. Forms act on vectors to give a number. Forms have a basis omega I defined by this, and forms can be expanded in a basis like this here. Forms can be expanded in a basis in this manner. I can expand vectors in vector basis EI. I can expand forms in form basis omega j. Yeah. So to make yourself comfortable, every time you want to imagine forms, imagine vectors. It's a dual space, you know. There's a duality. Whatever, although it's true that we are thinking of covariant vectors as forms, covariant vectors you can think of as dual to vectors. So it's just that we are not taught forms, one form, the differential forms often. We are more comfortable with vectors, but it's the same language, you see? Yeah? Okay, so now it gets very interesting. We have a picture of a gradient of a function. Given a function f, I know of its gradient as, suppose I have coordinate components I, j, k, coordinate directions, del f by del x I plus del f by del x j plus del f by del x I k, right? That's my picture of a gradient. Now, slowly we want to think of, and the gradient is a vector. So, let's go slowly. Let's recall f is a function. Let's say the function is defined on a space. Maybe I do a little bit of change of the screen. Suppose I have a two-dimensional space xy, and on this there's defined a function f of xy, and I am at some point, some particular point in this two-dimensional space. Let's say so it's a surface. Yeah. I want to know how f changes in different directions. As you go along y, f might change in a certain way. As you go along x, f may change in a certain way. So I take some vector v and I ask how f changes along v. That quantity I define as gradient of along vector v of f. That's the meaning. So how, because f is a scalar, where's the vector coming from? The vector is coming from saying that this object, grad v acting on f, grad v acting on f is the rate of change of f along v. This object is defined, is going to be grad f dot v vector. Okay? Sorry, what I want to say is the magnitude of this quantity, because this is a vector, right? grad v of f is a vector whose magnitude is going to be given by this dot product. Okay, so we will. So I hope you get the picture. Now I want to go back to the slide. Grad v of f is the rate of change of f along the vector v. Grad f is the rate of change along that direction along which the rate of change is the maximum. Grad vf is the rate of change of f along vector v. Suppose v happens to be that vector along which grad v of f is maximum. So v and grad v of f, if they are in the same direction, then this is grad f mod v cos theta. If both those things are in the same direction, cos theta is 1, theta is 0. So grad f is the rate of change of f along that direction in which the rate of change is the maximum. So maybe it's just too much. I'll go through it again slowly. Right. Recall grad f on a surface, 2 dimensions, equals del x f del y f is a covariant vector which points in the direction of most rapid increase of f. Its magnitude, the magnitude of this vector equals that maximum rate of increase of f with distance as we move in that direction. In other words, as I wrote, grad v of f is grad f dot v. This is mod grad f mod v cos theta. So the rate of change of f along the direction v is given by this number, mod grad f dot v equals mod grad f dot v. So grad f is a vector. Grad f is a vector, v is a vector, and if v and f are along the same direction, that's when you get the maximum. Cos theta will be 1 because theta will be 0. Grad v of f, its magnitude will be then grad f mod if you take v to be a unit vector. Okay? You get that picture? Is that okay? Okay, now we want to go to the how to express grad f as a one form df. So d bold will be df will give me a one form. This d bold operator, this object is called the exterior derivative. Yes, so done yesterday probably, yeah? Yeah? Okay. So d is called the exterior derivative. df will be a one form which is related to the gradient, grad f. That's the picture we have to develop slowly. Let E1, E2 be the standard orthonormal basis along the x1, x2 equals xy. Just a change, keep track of the notation. I have the xy plane, x direction will be called x1, y direction will be called x2. Let delta f be the small change in f resulting from moving along the vector v given by delta x1 E1 plus delta x2 E2. In the diagram that I showed you, move along a vector v which is defined like this. It's a small vector, delta x1 time unit vector E1, delta x2 time unit. So what will be the change in f? By definition, delta f will be del f by del x delta x plus del f by del y delta y, and this is grad f dot v. You see that, no? By definition, grad f has components del x f along x, del y f along y, and if you do grad f dot v, where v is this guy, if you do grad f dot v, you will get this. This explains the above interpretation of the gradient vector. Yeah, grad f along v will give me the rate of change of f along the v direction. The gradient one form exterior derivative of f is defined by its action on vectors. One forms act on vectors. The one form df acts on the vector v to produce the number grad vf. This is important to remember. Grad vf, this object is a number. Grad f is a vector. Grad of dot product v is a number. Is this number. Grad vf is a number. So I think you intuitively get the picture, right? df is the one form which acts on a vector f to produce the rate of change of f along v, and you know how rate of change of f along v is related to the gradient. So soon we will remove the v. Is this okay? The definition of the gradient one form. This is first introduction to the exterior derivative. It will live with us now through and through. This will be a very, all differentiation of forms will be done using the exterior derivative. And we will see this very nice result. Whenever the exterior derivative acts twice on a form, the answer is always 0. D square, D bold square is always 0. That's the beauty of this exterior derivative. We will see that. How to interpret dx equals dx1 and dy equals dx2. So let's see what is the meaning of this object. Exterior derivative of the coordinate components x. So this exterior derivative is acting on a function to produce a one form. Later on we will see how exterior derivatives act on one forms, two forms, etc. Exterior derivatives act on forms, on p forms, and the scalar function is a 0 form. Yeah, that's the exterior derivative question. Is df of v related to the directional derivative? Yeah, df acting on v is grad v of f. So in that sense, yes, is the directional derivative of f along v. Right. So the exterior derivative acts on functions. What if that function is just x1? Okay. Now dx acting on v. Yeah, dx. Right. This is a one form dx acting on v is equal to, look at this definition, grad v of f. It is grad v of x. Okay, the function is x, where x has components x1 or x2. So this is grad of, now expand v in the basis e1, e2, grad v1, e1 plus grad with respect to this vector acting on x by linear properties of the one form. You will have v1 pulled out, grad e1 of x. What will grad e1 of x do? It will pick up the x, only the one component of the vector. So let's come back. Let me see if I have more on the next slide. No, I have to explain this using here. So let's try to understand what is this. Okay, df acting on v is grad v of f. Now what is my f? My f is this quantity x which has components x1. I think I should have written x1 here. This is just dv of x1. dv of dy of v is v2. dx. Yeah, okay, I understand the confusion. Right, it is here. Here, this is the confusion. X is the same as x1, y is the same as x2. So this x is actually x1. This is a little bit of muddling of the notation. So grad v1 e1 plus v2 e2 acting on x1, right? So my function is now x1, let's say. So what should I do? What is this object? Grad v acting on x1. Let's see, where have we defined it? The rate of change of x1 is non-zero only along E1. Okay, are you clear getting what I'm saying? Maybe x1 and x2 or x and y are my coordinates. If I take a gradient along E1, only x1 is changing along that, and that is 1. Yeah, del x by del x is 1, del x by del y is 0. So that is why this object is just v1. Do ask me if it is not clear, just say stop. Is this okay, or are you lost? It's okay now? Yeah? What this is measuring is rate of change along this vector of, let's say, x1. So how fast is x1 changing along this vector? It will change only if you move along E1, obviously, no? And this V1 coefficient, because of the linearity of action of one form, will just come out. Okay? So, let's see if you, similarly, dy acting on V is V2. So, what did we do? What did we do? Right. Huh. Where, who's talking? Slide 3, yes.
You wrote that V operating on omega equal to omega v.
Where am I? V operating on?
Omega, that vector operating on one form,
Ha.
but that relation is not holds good in the next slide.
Do we have a vector acting on a one form in the next slide?
df operating on
Dx is a one form.
df is one form and d is the vector.
Yeah.
So df d not equal to df. So that relation.
I am making a contract. No. The thing is, V acting on df is by definition df acting on V. I have not independently talked of V acting on df. If you want to act V on df, please act df on V. And whatever you get, that by definition is the number V acting on df. How will how else can I act V on? V acting on a gradient is,
That is like v dot grad. That's different grad. Gradient of f and f dot gradient.
F dot gradient has to be defined as, this is a definition.
This is a definition, but this is only in that part df.
So let's see, you are saying df acting on V and then V acting on df.
These two are not similar.
I should not act on V on df without using that definition. What is the meaning of V acting on a gradient? I should use that definition.
V is not grad, no. V is exterior derivative that we have defined. So you are, I think, confusing between gradient of f into dot v and t. So that is not. This is the definition.
df is gradient of f, right?
No.
df is acting on a vector and defined like this, and grad vf is a number which is related to gradient of f by this relation. df acting on v is grad v of f. Grad v of f is related to the gradient by this relation. Confusing, is it? Let's talk more, yeah? You can come to me after the lecture. So what is our result? The gradient one form dx acting on a vector v picks up the v1, the xth component of v. Dx of v is v1. Okay? Similarly, dy of v is v2. Therefore, dx dy is the dual basis of E1, E2, and we already have talked of a dual basis, that is dxi ej is delta ij. That's what we were getting after. So let's go slow. Why is this interesting? The gradient one forms make a dual basis corresponding to the vector basis. Decomposition of a one form phi in the dual basis is phi equals phi j omega j, and phi j is phi ej by definition, and omega j is dxj. So that's what we are getting after. Are you getting the hang of it? Given a vector basis Ej, the dual one form basis is dxj. Yeah. So I could stick to the one form basis omega i's, but it gets better than that. Why not use these gradient one forms as basis? This is the given coordinates x, y, z form make the gradient one forms dx, dy, dz. They form a basis which is dual to the vector basis. So let's stare at this once again. Dx acting on v by definition is grad v of x because of this definition. Okay, the function is f is x, and grad v of x is by definition this object, and this is basically measuring the rate of change of x along a vector, but that rate of change will be non-zero only if the vector is along the x-axis, in which case this by linearity this v1 just comes out. Okay, so dx of v, question? Okay, yes sir, it is clear, thank you. Okay, so that is why these are basis one forms. Dx of v is a basis one form because it picks up the corresponding component of the vector. Okay, so omegas were introduced. We introduced this one form basis omega. Now we can make it more special. The dual basis of omega to E, the vector basis, the dual basis is nothing but the gradient one form. They form a dual basis to the vector space. So I suppose I have a plane xy, let's say x. Okay, suppose I have a plane xy. You have basis vectors ex or ex and ey, or e1 and e2. Make the gradient one forms dx and dy. Okay, those are basis one forms corresponding to the original vector basis. I think that is okay. Maybe take some getting you. So we can talk about. You can come afterwards. We'll try to work this out. Now, the gradient of f is a one form. Take phi to be that one form. Phi is df. Now, write df as, I want to write components of df. Components of phi are phi acting on ej. Now my phi is df, the components are df acting on ej, and this is how I write components of phi, no? Phi components of phi ej dxj. So here phi is df, these are components of df dxj, and df acting on ej by definition, df acting on ej is the gradient component del f by del xj. Is this okay? Let me show it to you again. Right. df acting on v is grad v of x. So df acting on ej is grad ej of f, which is nothing but del f by del xj. Right. And so right gives the gradient. So now this is very explicit. Why is this a gradient one form? Because of this. Its components are so clearly the gradients components in the one form basis dxt. So now we how do we write grad f? Del f by del x I hat, del f by del y j hat, del f by del z k hat. That object is actually this object, thought of in the language. It's a covariant vector, thought of in the language of one forms. The gradient one form df can be written in a component basis like this. So these are my basis one forms. Okay? Now move on. Definition of a tensor. A tensor of rank fv at a point P in space, in the base space, is a multilinear function of f1 forms and v vectors. Namely, this tensor T, which now is to be thought of in a coordinate independent way. Shown in this bold T, it's a coordinate independent picture of a tensor. It acts on one forms phi1, phi2, phi3 up to phi f. So they are f1 forms. And this separation symbol just separate, this is just a symbol separating forms locations from vector locations. It acts on f1 forms and on v vectors v1, v2, v3 up to vv. This is the definition of a tensor, and this will produce a number. Just as a one form acting on a vector produces a number, a tensor acts on a mixture of one forms and vectors. A one form acts on a vector, a tensor acts on vectors and one forms to produce number. That's the definition. And now we relate it to what we normally think of as tensors. So do that slowly. Let's multiply two one forms. This is a so-called direct product or tensor product, phi tensor product psi. These are two one forms. So they should act on a pair of vectors, right? Is identically this object, phi of v, psi of w. V and w are vectors. Phi is acting on v, psi is acting on w. This is the definition of the tensor product of two one forms. This is the tensor of rank 0, 2. Obviously, no forms but two vectors. This is one, all tensors are not direct products of one form. They can be defined in a more general way. But this is a special case of a tensor of rank 0, 2. What are the components of the tensor T, a second rank tensor, rank 0, 2? So this is the tensor of rank 0, 2. Its components are defined to be these quantities. T acting on the basis vector pair EI, EJ. Very obvious, no? A tensor acts on vectors. If you act the tensor on unit basis vectors, whatever number you get, those are called the components of the tensor. Okay? So let's see. Tensor T acting on a pair of vectors V and W is T acting on, make a basis expansion of V, make a basis expansion of W. Now, what has happened here? Vi, what did I do here? Vi, EI, Okay, Vi Ei is dxi acting on V, and Wj Ej is dxj acting on W. Let's try to understand this. This is a gradient one form acting on a vector will pull out the ith component. This is Vi Ei. Do you see this? Stop me. Dx acting on V will give me the Vx component, the first component. Right? How do I see this? There's something like here. Phi is phi j omega j, phi ej dxj. And what is phi ej? If phi is now dx, if phi is this one form, these are one forms. Okay. That will be a different one form, no? It will give you a different number.
So why is it defined it like that exact order, phi of V?
Order is important. Phi tensor product psi acting on VW will give you the number phi V psi of W. If you act it on WV, you will get a different number, phi. But this is a general, I didn't understand.
Is it like a notation, the first term in the first bracket?
Yes, you are right. The first form should act on the first vector inside the bracket, yes. When we do two forms where it is antisymmetrized, then it becomes simpler, yeah. Okay. So this is the definition of components of T, Tij. This is the definition. Now I want to see this little more. I want a coordinate representation. I want a basis representation for this vector T. I want to write it in components. And so since it is we are acting on two vectors, it is like it should have two. It should be expanded in this basis dxi dxj, because this basis has to act on a pair of vectors. So let's see what's going on here. T vi ei wj ej. T ei ej is this quantity. So what is left inside? Vi and wj. Vi is this object, Wj is this object, and I want to understand why this is Vi. Dxi acting on V. Let's see. Here. Question. Difference in the usage of square brackets and parentheses on the third line from the bottom. Okay. Okay, the square brackets are just temporary. Okay, what I am trying to say, T of Ei Ej is this component, then I am left with Vi. I am left with Vi. What is Vi? Vi is this object, dxi of V, and I wanted to justify that here. Vi is dx of V. We just proved that. Dx acting on V will pull out the ith component of V. So that's the result we are using here. This is Vi. This is Wj. And so this is a pair of one forms, dxi and dxj acting on a pair of vectors V and W. So I get a direct product dxi, direct product dxj acting on V and W. And V and W are arbitrary vectors. Remove that from the notation, it's understood. The first point and the last point together tell me This is how I write a tensor of rank 0, 2 in a basis. So if the tensor of rank 0, 2 is acting on a pair of it's acting on a pair of vectors, so its basis should be in terms of one forms, and that basis is this direct product dxi. I think it's okay. Are you okay with this? Please ask. As I said, just takes little getting used to. Everything is written here, and you have access to the slides, no? Yeah, so you can download it. So this is a nice way of taking a coordinate independent representation of a tensor and writing it in terms of its components and a basis. This is what we usually talk of Tij as the tensor, and we know how to transform. We'll see that transformations here, but this exactly is what is meant. But this is not very profound, you see. It's just an extension of this. A one form is expanded in a basis like this. A tensor with two lower ranks, with two lower indices, as acting on a pair. This is acting on a vector. This is acting on a pair of vectors. So instead of dxi, I have this direct product dxi dxj. That's what's happening. Yeah? Similarly, if now you had a tensor which was of the rank 2, 0, a tensor of rank not 0 to 2, 0 will act on a pair of one forms. So it will have upper indices t upper I j, t upper I, t upper j, and this will be ei direct product ej. You see? Do you see that? The dual basis to E1, E2 is dx1, dx2. When you expand some, depending on whether these are upper or lower indices, you will have a combination here of dxi's, dxj's, ei, ej. Is that okay? As a special example, the direct product of phi and psi is phi I psi j dxi dxj. Okay. So do you see that? This is a special case of this. But not all second rank tensors are direct products of one forms. You see that? This one was not a direct product of one forms. How many components does this tensor have on an n-dimensional space? Tij number of components? Please tell me. N square. And this object? N for phi, N for psi, 2n. They are getting product multiplied, but 2n numbers are enough to so n square versus 2n. N square is much larger than 2n. So all second rank tensors are not direct products of one forms. Direct products of one forms produce tensors, but not all tensors are such direct products. That's very obvious, no? Okay, I think as I said, you get used to it slowly. Takes some time, but afterwards it's very intuitive.
So why it is dual, like if I am not wrong, it is getting summed over I and j are the dummy indices.
Yes.
So I runs from 1 to n and j also.
Yes.
So that makes it 2n.
Yes, that's right. But here this is Tij, and this is n square, yes. Okay. Similarly, we can have tensor products of two vectors, V direct product W. Now these vectors act on a pair of forms, and analogous to this relation, in analogous to this relation, where are they? Yes, in analogy with this relation, if you have a direct product of two vectors, you will write a equation like this, okay, like this in the first line. And for a tensor of rank 2, 0, you will write something like this, and then you can have mixed tensors also, and you just formally write the direct product of omega dxi's and ej's. Metric as a second rank tensor, not yet in terms of forms, but a metric as a second rank tensor. Later we will see how to talk in the language of forms also. This we understand, right? The line element in two-dimensional space labeled by coordinates u and v is E du square plus 2f du dv plus g dv square. Make this formal substitution. U is x1, v is x2, g11 is E, g12 is f, g22 is g. Then the second rank tensor of the form, so what is it? It has to act on vectors. So we'll do the other one also. This tensor of rank 2, 0, is it correct? It is lower, so it has to act on vectors, right? Yeah. This has to act on vectors, so it's a tensor of rank 0, 2, okay, and it will be denoted like gij, dxi, dxj. So what is going on here? That this du square is basically dx1 direct product dx1. That's what this du square is. Du dv is dx1 direct product dx2, and so on. So the metric is now defined as a second rank tensor, and this is its basis. So this is a special case of this fellow. T is Tij dxi direct product dxj. It's a tensor of rank 0, 2 because it's acting on two vectors. If it is a tensor of rank 0, 2, its basis will be in terms of forms, because forms act on vectors. So if it's acting on vectors, the basis is in terms of direct product of forms. A special case of T is now this second rank tensor G, whose components are Gij, and this is its basis. What's the definition of a contraction? Given a tensor A of rank 2, 0 and a tensor B of rank 0, 2, define, this is the definition, define quantities Cik as Aij, Bjk, where J is summed over. Aij and Bjk are components of A and B. We have just figured out how to define components. Cik are components of a new tensor of rank 1, 1, defined like this. So if you have two tensors, one of rank 2, 0, one of rank 0, 2, you contract them. One upper index will reduce, one lower index will reduce. You will get a new tensor of rank 1 down from the upstairs, you will get a new tensor of rank 1, 1, okay, which is mixed, so its components, right, so acting on, which is defined by action on one form and one vector, and that action will give me, for example, this object Cik, phi I, Vk, and the Ciks are this formal way of saying what a contraction of two tensors is. Okay. Now formally understand how the metric is used to raise and lower indices. Okay? Changing rank using a metric tensor which has a rank 0, 2. Okay, it acts on two vectors, so it has a rank 0, 2. Okay, what does that mean? If we leave one slot of G open, G has two vector slots, leave one of them open, in the other one insert a vector n whose so like n is a vector, I want to lower the index. So n has an upper index, I want to, so suppose ni is the component, ni upper. I want to know what is ni lower, it is gik nk. I want to get that in this language. If we leave one slot of G open and insert the vector n into the other, we get a unique one form omega corresponding to n. So, what is meant by raising and lowering index? You are changing a vector to a one form or a one form to a vector. Here we are changing a vector to a one form. How are we doing that? G has two vector slots free. In that, one of the slots, in the second slot, put n, the vector which you want to, whose index you want to lower. You will get n is mapped to a one form omega of v, which is defined as g of v and n. V is arbitrary. N is the one you are interested in. G of Vn gives you a one form omega of v, where G is the metric tensor. Omega of v is the one form corresponding to v, which one form corresponding to n, which means you have lowered the index. So let's see how this may look very formal. Omega I will expand as ni dxi. By this is my definition, by notation, this is the expansion of omega. Now I want to prove that this is true. Ni is gij nj. So you may think, what we are hammering to get something that we already know. But we have to go through this process to understand what the tensor does. So I want to prove something that you already know, that index lowering is done using the metric tensor, but index lowering now changes a vector to a one form, and I want to see how that's happening. Omega is ni dxi, this is a basis expansion. Ni is defined as omega ei, right? That is the basis, that's the definition of ni. Omega ei is defined here. It is g ei n. G ei n is g ei nj ej. Nj comes out and this is gij. It looks like magic, very simple. G ei ej is by definition gij. Hence, we see the metric can be used to change the rank of a tensor. Yeah? That's it. Say from 1, 3 to 0, 4. Suppose it's 1, 3, the 1 will be lowered, so that will become 0, 3 will become 4. So we do that, for example, with the Riemann tensor, for example. The Riemann tensor is a tensor of rank 1, 3. 1, 1 form, 3 vectors. So it's a tensor, it has 4 indices. 1 one form index, 3 vector index. The components r, I, j, k, m. Okay? So because it acting on 3 vectors, 3 are lower, it's acting on 1 one form, so 1 is upper. Convert it into a tensor of rank 0, 4. This is a tensor of rank 0, 4, defined as the same tensor which was originally a rank of 1, 3. These are the same tensors but written in different ways. So the left hand side, this fellow is defined like this, and I want to get rid of this NL. The right hand side is this object. This is the object on the right hand side. Okay. And I substitute for Nm because I know what Nm is. Nm is GML NL. So you see now the U, V, W, N are all arbitrary. RIJKL is RIJK, RIJKM upper, GM and GM. Right. So remove the U, V, W and N. RIJKM upper GML is RIJKL. Yeah? So this is formally what has happened. Similarly, you can define inverse of a metric tensor which converts a one form into a vector. It raises index. Need a tensor G tilde of rank 2, 0, taking two one forms as input and yielding a one form omega, two one forms are inputted, one of them is the one of interest omega, and you should generate the corresponding vector which has now upper index, that is this object G tilde phi of omega, and just repeat what we did in the previous slide. Ni upper is G tilde nk, G tilde ik nk. So I have taken a one form and generated a corresponding vector by raising indices. Note that G tilde is uniquely determined by G. How? Start with a vector n, act G, generate the one form omega. You have raised the index. Now lower the index. Omega acted upon by G tilde. You lower the index, you will get the same vector. So obviously G and G tilde are inverses of each other. In other words, Ni upper is G tilde upper ik nk lower, G tilde ik and lower one goes like this. In other words, this has to be, the product has to be a delta function because they are inverses of each other. So getting to be time. So I hope you get this. And normally we don't show this tilde, we ignore the tilde. G ik upper is the inverse of G kj lower. Okay, now moving on to two forms. A two form is an antisymmetric tensor of rank 0, 2. This is the definition. A tensor of rank 0, 2 acts on two vectors. If this property is satisfied, now this is related to what one of you what you asked, that if you interchange V and U, do something different, right? Here this is a particular case when the interchange changes the sign. So this is a two form. Not all tensors are two forms. All two forms are tensors, and there is a good reason why antisymmetry is brought in when we go from one form to two form to P form. A P form is a completely antisymmetric tensor of rank 0p. Any two vectors, so there will be like, instead of two there will be many. Any two you interchange, the sign has to change. That's a completely antisymmetric tensor of rank 0p, that is a P form. Okay. The highest P form that can exist in an n manifold is an n form. That is clear, no? Because you put, if you have n plus 1 indices, then clearly one index is repeating, and interchange should not do anything, but here it wants change of sign. So those components just vanish. So it's meaningless. The highest P form that you can have on n manifold is an n form. And what is the highest n we typically work with? Is 4. So in 4-dimensional space-time, 0 form is a function. 1 forms are like vectors, dual to vectors. 2 forms we'll see are areas. 2 forms are areas. 3 forms are 3 volumes. 4 forms are 4 volumes. This all we'll deal with. 0 form, 1 form, 2 form, 3 form, 4 form, and these are always antisymmetric. That is going to be our machinery. Let me see if I can push little more. Right. So I will steal a few minutes if you don't mind. I don't think I'm going to the end, but let's see how far. An example of a two form is the area two form AUV, oriented area of a parallelogram with edges U and V. On a two-dimensional space, xy plane, draw a vector U and draw a vector V, some angle apart. If you take U cross V, that gives you a cross product vector. Let's say if you are in three dimensions, just taking that example, or even without that, if you have a parallelogram with edges U and V, its area will define, we'll see that slowly. What is its area? Okay, best go think of in three-dimensional space, you draw a parallelogram. The area of the parallelogram is U cross V. That's correct, no? Right? So, but now think about it. U cross V is a vector. And we are saying the area is a vector whose magnitude and the magnitude of that vector is mod U mod V, what is it, sine? A cross B.
Cross is sine.
Cross is sine. A cross B is mod A mod B sine of that angle in between. So that is a vector with some magnitude. Well, how come an area is a vector? Yeah. So area is actually a two form. So we'll see how this two form is related to that vector. That is, we'll do that. So I'll justify why area is a two form. The wedge product of two one forms is by definition phi wedge psi is phi direct product psi minus psi direct product phi. So notice that already this is acting on UV. If I interchange U and V, this two form has to change sign. And if I interchange phi and psi, then also it changes sign. So there are two antisymmetries. By definition, this is the definition of the wedge product. We will also soon see what is the physical interpretation of the wedge product, why it is so important. So I have just introduced it. The wedge product builds forms of higher degree from forms of lower degree. So phi and psi are one forms. Phi wedge psi is a two form defined like this. On a plane, consider Cartesian basis one form dx dy. Then dx wedge dy is the area form. Why? Dx wedge dy acts on, let's say, a small vector del x e1 a vector v whose components are del x e1 del y e2. What is this by definition? You'll use this definition. Dx acting on e1 will give me delta x, dy acting on e2 will give me delta y, dx acting on e2 will give me 0. Right? So dx is a gradient one form acting on some other. So this is just delta x delta y. So this is why this is called a area two form, because it generates the area of that space. More generally, dx dy acting on uv, not just this, acting on uv, is by definition this object. This is the wedge product. It is this acting on vector u1, vector u, vector v. Okay. Now dx acting on this vector will pick up u1, dy acting on this vector will pick up, dy has to act on the second vector, will pick up v2, and similarly dy acting on this vector will pick up u2, and dx acting on this vector will pick up v1. So that is this fellow, which is the determinant, and this clearly is the area, right, is the cross product. right? So this is how you define the area 2 form. So I think, should I stop here, because is it okay to stop here? Let's see what is left. Interpretation of the wedge product, basis 2 forms, dot product and vector product understanding using forms, and Faraday some connection. So this is quite basic. I think we should be able to do it tomorrow. And okay, I'll stop here. Is this going too slow? You are okay with the speed? Anybody thinks this is too slow, please say so. You okay with the speed? What do you say? It's all right? Yeah. Before the course ends, we'll write down Einstein equations in the language of differential geometry. That is the goal. We'll definitely get there. Maybe we'll do more than that, but at least that much, At least that much we will do. Okay, thank you. How do we assign directions, orientation of a volume element? Very good. A volume element I'll do tomorrow. So what will be just foreseeing, right, like if this is a volume 3 form, if this is a volume 3 form, the directions will depend here, because if you interchange x1 and x2, that will change sign. So if it changes sign, the orientation changes. Yeah. So whether you are doing dx wedge dy, whether you are doing dy wedge dx will change sign. We'll see that tomorrow.